Okay. Hello, everyone. Thank you for joining this session. My name is Takuya Namae from Sony Group Corporation. This is my first time speaking at Open Source Summit. So today, I'm excited to introduce Project ESSTRA. It's a tool designed to improve transparency and traceability in the software supply chain. Let me talk a little bit about myself. I joined Sony in 2003. I've worked on various software projects, such as a web browser and the EPUB 3 bureau. Later, I started working on open source license compliance after investigating the licenses in Chromium. Later, I started working on, now I lead compliance work for Linux-based system software used in many Sony products. We handle over 500 source packages every year. I also lead the development of related tools like ESSTRA, and I teach a practical course on this area inside Sony. Here is today's agenda. We start with a short introduction, then move on to the background and the goal of this project. Next are the challenges and the solutions it provides. We'll go through its key concept, technical overview, and real-world use case. Then we'll look at the impact, why it was open sourced, where to get it, and future work. Q&A session is prepared at the end of this talk. Let's start with a simple question. When you use open source software, do you ever wonder which source files were actually compiled into the binary? This is an important question, especially when we think about license compliance and security. If your answer is yes, then this session might be helpful for you. ESSTRA is a tool that collects the information about source files actually used during the build process. It works with GCC and embed that information directly into the binary. This includes file names, licenses, and other related metadata. ESSTRA was open source last year. This helps people in the software supply chain, from upstream developers to downstream integrators, to understand what's inside the binary and share that information clearly. So now, let me explain why ESSTRA was needed. In recent years, SBOMs, software bills of materials, have become important. And SBOM is a list of source components included in a product like a bill of ingredients for software. As software gets more complex, we need better transparency and traceability. SBOMs help identify vulnerabilities and ensure license compliance. They are now part of global efforts like the US Cybersecurity Executive Order and the OpenGA ISO standard. To make SBOMs truly accurate, we need to know how open source software is actually used. This diagram shows how we usually use open source software in development. We get the software, build it, integrate it into our own software, and then release it. At the end, we create an SBOM to show what's included. Understanding this flow is a starting point for thinking about license compliance and traceability. You might link some open source libraries to your software, but that is just the tip of the iceberg, as you can see in this image. We rely on many components. Some we use directly, others come through layers of dependencies. This structure can be complex. For example, one library may depend on several others. Understanding this helps us see what's actually used in our software. Open source packages often include many files that you don't actually use in your software or product. These may be documentation, test code, or files for optional features. But when we create an SBOM or review licenses, we sometimes treat the entire package as if everything is included in your software. This can lead to confusion or unnecessary work. So what should we really list in the SBOM? When we create an SBOM, we focus on what is actually included in the software we deliver. In most cases, that means the source file that were compiled into the binaries. We may also include scripts or configuration files and so on, if they are truly used in the software. In short, what is included in your software is what should be listed in the SBOM. And what is listed in the SBOM is also what must comply with open source licenses. We don't need to review the entire source package, only the parts that are actually used in the software. This helps reduce unnecessary work and makes license review more focused and efficient when we deliver software or products to end users. From what we have seen so far, it's clear that we need to align three things: what's actually included in the software, what's listed in the SBOM, and what must comply with open source licenses. This alignment is essential, especially when we deliver our software to end users. Our goal is to make it accurate, efficient, and reliable, and we aim to achieve it through a technical approach. But achieving that goal is not easy. From our experience, the hardest part is understanding where each binary really comes from. In many cases, we don't know which source files were actually compiled, unless we check huge build logs or the makefile carefully. This makes license review difficult and sometimes risky. That's why we believe this is a key challenge. And it's also the reason we started developing ESSTRA. Let me show you an example based on an actual case we faced. Imagine we want to use open source A in our own software. At the top level, we see files like README, authors, and license, and it looks like this project is licensed under X. Before integrating it into our software, we ran a license scanner on this package. And the scanner found not only license X, but also license Y and Z. That raised the question, where did those extra licenses come from? The package had directories like doc, test, and source. But we couldn't tell which files were actually compiled into the binary. So we were not sure whether license Y and Z were really part of the final binary. Here's another case that shows how things get more complicated. This time, we are looking at open source B, which generates both an executable and a library. The executable is licensed under X, and the library is licensed under Y. The source code is organized into directories like source, lib, and common. The scanner found license X in source directory and license Y in lib directory, which makes sense. But in common directory, it found both license X and Y. Now the question is, which files from common directory were used in the executable and which were used in the library? Without knowing that, we cannot be sure which licenses apply to each binary. So how can we solve the challenges we just saw? The key is improving traceability. We need to know exactly which source files were compiled into which binaries. For our Linux-based system software used in the Sony products, improving traceability was essential to keep compliance work both continuous and efficient. That's why we developed ESSTRA. The name stands for Enhancing Software Supply Chain Transparency and Traceability. It was designed to improve traceability in the build process and to support continuous and efficient license compliance. By embedding source file information directly into the binary, ESSTRA helps us solve the challenges we have seen, and in a technical and automated way. Let's now revisit what ESSTRA actually does with a concrete example. ESSTRA collects information about the source files used during the build process with GCC. ESSTRA then embeds that data into the binary. On the right, you can see a sample output from a binary built with ESSTRA. It includes file names, hashes, and license information. This metadata is stored in a dedicated ELF section and can be extracted later using a Python script. So you can clearly see which source files and which licenses are included in each binary. Let's look at some key concepts behind ESSTRA. By introducing them here, I hope this helps you understand ESSTRA more clearly, especially the thinking behind its design and purpose. The first concept is build framework independence and easy integration. ESSTRA collects source file hashes during compilation, independent of the build system. Typically, build systems manage the compilation process, but they don't offer reliable proof of which source files were actually used. ESSTRA filled that gap by ensuring file identity, even in complex or customized environments. In addition, it embeds metadata directly into the binary during compilation. So it travels together as verifiable evidence, regardless of the tools or CI systems in use. Many of you already have your own development environments and build systems. That's why ESSTRA is easy to integrate with minimal setup. It doesn't rely on large frameworks or special environments. The second concept is no impact on the execution of binaries and minimal changes to build settings. ESSTRA Core works as a GCC plugin and collects source file information during compilation. To enable it, you just need to add F plugin option to your build configuration. ESSTRA creates a dedicated F section called .ESSTRA, but it doesn't change the executable code or affect linking. The binary runs exactly the same with or without ESSTRA. This approach works with both production and debug builds. In production builds, ESSTRA avoids behavior changes caused by debug option. So it captures the actual source files used in the final binary. The third concept is structured metadata for SBOM use. ESSTRA is not just about collecting source file information during builds. It's about making that data useful, especially for SBOMs and compliance workflows. To support this, ESSTRA records source file information in YAML format and stores it in the .ESSTRA section of the binary. The metadata include file names, hashes, license information, and so on. It's compatible with SPDX and can be linked to other SBOM tools and existing compliance workflows. The fourth concept is retaining SBOM data in release binaries. Unlike debug information, the .ESSTRA section is not stripped during production builds. This means the metadata stays inside the binary and can be delivered together with the software. Embedding SBOM data directly into the binary makes it easier to track, verify, and share, especially when distributing your software to external teams or customers. Depending on your role in the software supply chain, you can choose how to handle the metadata. For example, an upstream developers can pass along binaries with embedded metadata, while a downstream integrator may choose to remove it before shipping a product. The fifth concept is post-processing support for additional metadata. ESSTRA provides a UTT tool, a Python script, that allows you to update or remove the .ESSTRA section in the binary after the build. If you have additional data, such as license or vulnerability information, you can link it to the source file data already embedded in the .ESSTRA section. You don't need to rebuild the binary. Just run the update command in ESSTRA UTT. This flexibility makes it easier to enrich the metadata based on external sources such as an SPDX or review results. That concludes the 5 key concepts behind ESSTRA. From here, I'll start explaining the technical details. Let's begin with how it works during compilation. ESSTRA core is implemented as a GCC plugin. It can be enabled by adding a plugin option to your build settings. After it's enabled, it flips into 2 important callbacks. The first is plugin include file callback to detect the source files being compiled. The second is plugin finish unit callback to create a new Elf section and embed the metadata. ESSTRA creates a dedicated Elf section called .ESSTRA, and it contains a list of the actual source files used in the binary. This section is first added to each object file during compilation and later merged into the final binary when the linker combines all object files. In addition to collecting source file information, ESSTRA can also embed related metadata, such as license data. For this, we use ESSTRA UTT, which is provided as a Python script. If you already have license information for each source file, you can use the update command to add that data to the binary. This process happens after the build, so you don't need to recompile the software. ESSTRA UTT also provides other commands like show command to inspect the metadata and rm command to remove it if needed. Now let's talk about .ESSTRA section itself. ESSTRA stores metadata in a dedicated F section. And for now, we are using section header type progbits. We looked at other options like .node and .debug info and considered different technical and practical aspects. In the next slide, I'll explain why we decided to go with this setup. There are several reasons. First, it keeps a clean separation from other sections and does not affect executable code. Second, it supports a structured format like YAML, which are essential for SBOM data. For example, the .NET section uses a fixed format and needs custom handling for SBOM, making it hard to extend. And the .debug info section is tied to dwarf, very complex, and usually removed in the production builds. With the .ESSTRA section, SBOM metadata can stay in release binaries, not just in debug binaries. At this stage, we use a dedicated Elf section named .ESSTRA, but if a standard like .SBOM appears, we would be happy to migrate to it. Based on these points, we believe this setup is a better choice for now. Okay, so let's look at your use case. This example shows how ESSTRA fits into an actual workflow. The process has 4 main steps. Step 1, to build and install ESSTRA core plugin. After compiling the ESSTRA core source code with make, we install it into the GCC plugin directory. Then we update the GCC spec file. This file defines the default behavior of GCC. So by adding ESSTRA core there, the plugin loads automatically during every compilation. Once this setup is complete, ESSTRA is applied by default. So we don't need to edit OpenSSL's build files to add the F plugin option. Step 2 is to build OpenSSL using ESSTRA. We download the source code and run configure and make, just like a normal build. Because we updated the GCC spec file in step 1, the ESSTRA core plugin is loaded automatically. We don't need to change any configuration files or build step script. After the build, we check the binary with, for example, readelf command. It shows a new elf section. This confirms that ESSTRA has embedded the metadata without any extra changes to the build process. After confirming that the .ESSTRA section exists, we can inspect its contents. For this, we use ESSTRA UTT and run the show command. it extracts the metadata from the binary and displays it in YAML format. The output includes a binary name and a list of source files that were actually compiled. This gives us a clear view of what is inside the binary without reading huge build logs or the makefile carefully. And step 3 is to analyze the licenses of the source files. We use a license scanner like Fossology to create an SPDX tag value file. This file includes the declared licenses using the tag license info in file, and it also records a hash value for each file. ESSTRA metadata has the same hash for every source file, so we can map them accurately. Right now, ESSTRA uses SHA-1 by default. The reason is that SPDX version 2, which is an ISO standard now, requires SHA-1 in its specification. It's also lightweight and practical for checking file identity. Of course, there is growing interest in stronger hashes, and SPDX version 3 recommends SHA-256, which is already supported by ESSTRA, so it may become the default in the future. Step 4 is to add license information into the binary. We use the update command from ESSTRA utility together with the SPDX file from the previous step. This command merges the license data into the .ESSTRA section of the binary. After that, we run the show command again. Now, each source file in the .ESSTRA section includes its license information. This completes the link from source file to binary and finally to license. That's all for the OpenSSL example. Let's revisit the challenges we saw earlier. In both case studies, we couldn't tell which source files were actually compiled into the binaries. With ESSTRA, we can now solve that technically. For example, we applied ESSTRA to 187 Debian binary packages used in our Linux-based system software. The total number of source files in the corresponding source packages was about at least 350,000. But only around 30,000 files, just 8.8%, were actually compiled into binaries. This means ESSTRA helps us clearly separate what's included from what's not. As a result, license analysis becomes much more efficient and accurate. Here, I want to explain why we open source ESSTRA. One reason is to help original authors check that unintended files are not included in their binaries. By using ESSTRA across the software supply chain, especially from the upstream side, we can improve the quality of open source software itself. On the downstream side, it also supports compliance with open source licenses and keeps projects aligned with regulations. All of this will raise the overall quality of SBOMs throughout the supply chain. We hope ESSTRA will be useful for many working with open source software. ESSTRA is now available in several ways. As I mentioned earlier, the original source code is on GitHub, so you can get it from there. But that's not all. Last month, ESSTRA was packaged for Debian, and as a result, it's also available in Ubuntu. This was possible thanks to a great collaboration with Hideki Yamane, a Debian developer. When I presented ESSTRA at OpenChain Japan Community Day in March, he showed interest in ESSTRA and creates its Debian package and has continued to maintain it. So now you can choose the way that works best for you and start using ESSTRA. This collaboration with Hideki Yamane didn't stop there. We came up with an idea to apply ESSTRA to a large number of Debian packages all at once. To explore this, we ran a feasibility study to add ESSTRA-generated metadata into Debian debug sim packages. For a single package, only minimal changes are needed, as shown in the screenshot on the right. Of course, instead of modifying each package one by one, it would make more sense to handle this in a common part of the Debian packaging toolchain. And last month, we presented this idea together at DevConf 25 in Brest, France. We received a lot of valuable feedback from many Debian developers. It was a great opportunity to share our ideas, and we truly appreciate the thoughtful conversations that followed. If we focus on debug sim packages or debug builds, there might be other ways to achieve the same goal. But as I introduced in the key concept today, ESSTRA can work not only with debug builds, but also with production builds. So we want to leverage the flexibility to improve transparency and traceability for Debian packages and help raise overall quality. We will continue to work on this with Hideki Yamane and Debian community. Let me share some of our ongoing work and future plans. We are currently working on reproducible build support, including path normalization to avoid embedding absolute processes in metadata. We are also developing a linker plugin to optimize metadata by removing duplicates across object files. Most of the implementation is done, and we plan to merge it soon. And currently, this function is available as a shrink command in ESSTRA utility. At the same time, we would love to see more community involvement. We are exploring how ESSTRA could support other compilers like LLVM, Clang, Rust, and Go. This is still under investigation on our side, and we would really appreciate help from those with expertise in these tool chains. We are also interested in embedding vulnerability metadata in .ESSTRA. There's still a lot to do, and we are excited to move forward together. Before closing, I'd like to highlight some of the people who supported this project. First, Arman Helmer. He is here today. He gave us valuable technical advice soon after ESSTRA was open sourced last year and extended his bank tool to support it. Next, Hideki Yamane, as I mentioned earlier, he suggested that we present at DevConf, created Debian package for ESSTRA, and has continued to maintain it. And our OSPO team, who are also here today, they have always offered dedicated support, and their long-standing engagement in the open source community made the open sourcing of ESSTRA possible. And finally, I'd like to thank our team members, my colleagues in Japan and India, as well as my mentor and managers who supported this project throughout. That concludes my presentation. Thank you so much for listening. I'm really happy to take any questions, comments, or feedback. And if you could speak slowly and use a simple English, I would really appreciate it. Thank you. No mic. Sorry. Thank you. Thank you.
Can you hear me? Okay. Actually, I have 3 questions, but I think I can leave some of them for the outside. First, do you have any metrics on how using ESSTRA how significant it is, the footprint, I mean the resulting size of building, I don't know, an entire root file system with ESSTRA enabled. Were you able to perform this kind of test? Or were you using ESSTRA for very specific binaries?
What you are talking about, the size is embedded metadata size, or?
Yes, the final binary size, including the metadata.
Okay, I think it's, of course, it's depends on the source file, source code or binaries size, because how many source files are included in the binaries depends, affect to the size of binary. And currently, we are not sure the strict guidelines or something, right?
And do you count at some, because you already took this very noble initiative of including it in Debian, but did you ever think about including it in build systems such as build root and Yocto?
So what do you mean about it?
Including support for ESSTRA in build systems such as Yocto or build root. Is this a perspective for the future? Is this something that you plan on doing or that you would accept help for? Is that something in your interest?
You mean, is there any restriction or condition to integrate ESSTRA to build systems or something?
If you count on doing it at some point, or if you will stick with Debian?
Well, I can comment.
Okay. You want the mic?
Yeah. So Sony is a Debian shop, but we have nothing against Yocto. I don't know. So the question is, are we interested in seeing this integrated into Yocto or build root? And the answer is yes. We'd love to see it, taken up, but we don't have a lot of Yocto experience. So since we're not a Yocto shop, so any help in that area would be appreciated. Yeah.
Is it reproducible or not? The metadata that is produced by the tool is reproducible or not? So if you run the build with, I think it's not. If you run the build in different paths, it is encoded.
Could you speak more big? Sorry, it's hard to hear.
The question is the information reproducible? So like if you build it on a different machine, are you going to get different absolute paths? Yeah. So I think that's what the path normalization is about, is to try to fix that particular issue.
So it's one of the future work. So currently we are in absolute processes are including. So we have to change the this one. So if this we fix this one, then
all right. So I have a different question for you.
Okay.
Why include this in the binary? Attestations and SBOMs and other things that are usually generated at a different time are detached. They're separate files. And that has a lot of advantages to putting things into the binary.
Yeah, I understand. We cannot include all of SOM data into the binary, but we think, as I mentioned in the key concept, we think it's important for us to include the source file information, which is generated the binary itself. So if we manage the source file information and the binary separated, then we have to manage both data separately. So how should I say? Yeah,
they can become different. Is that what you're worried about? That you might have the wrong version of one versus the other? Because that problem is solved in a lot of the formats. That's one of the things that like in toto attestations and other formats try to solve. So I think if that's the reason to stick them together, I think you might be doing a lot of work you don't need to do in that case. Because if you in anything you do where you embed a signature, it has problems like if someone else wants to sign it, then typically that's problematic. Even if you support multiple signatures or multiple ESSTRA section formats, if I and someone else both want to apply an ESSTRA section to the same thing and we do it in opposite orders, we're probably going to end up with different binaries. And so in general, like most of the world that started with a lot of like embedded signatures and package formats moved away from that to detached signatures because they allow you to have any number of people sign. They're not brittle in certain ways. So I just want to raise that as something to think about. Maybe there's probably reasons that I don't understand.
Thank you.
Thank you so much. I absolutely love the concept. I'm the author of a binary SBOM tool called Blend, and definitely would love to check it out. I have a question though. It's kind of like security. So how do you deal with insider attacks threat? For example, because this binary section can be manipulated by anyone, somebody inside your organization can add or remove libraries. So I think some kind of signing verification part is missing against. Is that something in your roadmap?
Currently, it's one of option, one of future work. Currently, we supporting security and vulnerability is our one of concept. But currently, our investigation is not started yet. So yeah, we are. Also, I think how to handle these information for each source files. Maybe this should be handled as a, for example, binary units and so on. So, yeah, I think there's still some investigation.
Okay,
yeah.
Thank you.
Thank you. Anything? Okay. Yeah, thank you. Thank you for joining this session. Thank you.